All right, so we're going to be talking about audio codec technology, doing reliable audio transport over unreliable networks. Now, in order to discuss this concept, we got to do a little bit of an IP audio technology overview. For example, what is IP and what is IP audio? IP audio and broadcast, knowing about compression types, bitrate, compression, and latency, and the relationship of those three things to each other. Doing audio over a wide area network or public internet, which is what many folks are interested to know more about. We're going to talk about that. We're also going to provide you technology that you want to know about for doing reliable transport over these unreliable internet networks. And obviously, we wouldn't do this without presenting you some solutions and things that you can achieve. Now, the first thing I'd like to do is give everybody some context. What is the environment we normally associate with doing audio over a WAN or a wide area network? So there's really three areas to broadcasting. There's remote broadcasting, what you see over here on the left. The studio side of broadcasting, where remote signals are coming into some central location, being mixed or remixed or things being added to it. And then the program distribution side. So simply stated, we have remote, we have studio, and we have distribution. And we're going to refer to these when we talk about something being in remote broadcast mode versus something being in distribution mode. Distribution mode, as the name suggests, is doing something from one place to many. Web radio, a transmitter site, perhaps another studio or another location, or even satellite. So that's the context of doing audio over IP in a wide area network. So what is IP and what is RTP? Well, the first thing you need to understand is Internet Protocol. So basically, a datagram is a self-contained, independent entity of data carrying sufficient information, basically routing from one source to another. And the IP protocol is what we use to establish end-to-end communication over local area networks or wide area networks. And in these situations, there's always a best effort to deliver data, but it doesn't guarantee that all the packets will arrive. It doesn't guarantee that there won't be corrupted packets. It won't guarantee uncorrupted packets. It won't guarantee the order of received packets, and it won't guarantee that packets are not duplicated. So this is an important concept when we get into doing multimedia over IP. Now, we've all heard of a basic IP address, and basically there's one IP address per network interface. When I say network interface, I'm speaking of that Ethernet port on your computer. And it can be defined manually, a fixed IP, or automatically. So it's important to understand this concept because when we talk about redundant streaming, to do it right, you really want to have more than one network interface, and we'll talk about that in greater detail. So with the internet and with IP audio, before we had the ability to do audio over IP, we were just doing basic computer or loss-tolerant connections, and this is called UDP, User Datagram Protocol. In 1980, it's one of the core members of the Internet Protocol suite, and it's used primarily for loss-tolerant data. So if you've ever worked over the internet, done remote desktop or something like that, the mouse gets a little staggery or you lose connection momentarily, but you tolerate it because it's okay. It gets you through the moment. But it's not going to allow the receiver to detect missing or disordered packets, and it's not suitable as a protocol for doing multimedia over the network. So fast forward into the mid-90s, and we get into this idea of RTP. And you will run into this terminology. This is why we talk about this, so everybody understands. But from 96 to 2003, this was an IP protocol that was developed for delivering audio and video over IP networks. It runs over the UDP protocol, and it's used in conjunction with something called RTCP, which is a control protocol. So the RTCP carries things that are required for multimedia, things like transmission statistics, quality of service, synchronization of multiple streams. It contains sequence numbers and timestamps, so it allows from the encode to the decode, it allows the decoder to put together back that stream with nothing missing so that it's a perfectly good audio signal. Also, there's a concept in the world of IP audio called SIP, or it's a signaling protocol, and it stands for Session Initiation Protocol, and it's used in conjunction with RTP streams for establishing connections over a network. SIP is great because when two things come online, it allows them to see each other when they're registered properly and immediately connect, and the user doesn't have to know the IP address or the public IP address, so it's very convenient. Also, in the case of some technology I'm going to share with you, the SIP infrastructures can be very useful when you want to work with third-party codecs. So let's talk about broadcast streaming with IP audio. Here's what we know. We know that IP technology is used to carry audio. We know that RTP is our standard protocol. We know SIP is used to establish a connection over a network, and it's actually a very convenient protocol for us. But here's factors that affect audio IP: audio compression and the network bit rate, because that's going to determine the number of channels, sample rate, and require compression in order to get our audio smoothly over a network that might not be very fast. So why audio compression? Well, in order to use audio compression, we got to understand it. And the reason it exists for this is that it's to adapt the bit rate of real-time transmission over IP networks, and it limits the size of data to be transmitted. There's two types of audio compression: lossless and lossy. Lossless is nice because it has no loss of audio quality, but the weakness in IP audio is not a constant bit rate, and it has a very low average compression ratio, generally less than 2. So the broadcast industry for audio and video streaming has adopted various lossy compression algorithms because they have the advantage of a fixed bit rate, and it gives us good compression ratios that squeeze the information into slow networks, and it still gives us good audio quality. The weakness using compression, however, is as the more compression we use to fit into a slower network, we do add latency. So that's a relationship that you want to be aware of. So what are some of the compressions that you're going to run across in setting up a streaming situation? Well, for voice, for VoIP, for years we've been using something called G711 and G722. These are great because of the audio bandwidth for the voice is much narrower, so we can get by with very low bit rates like 64 kilobits per second. Now, to do complex or high quality audio, several algorithms have emerged over the years. You've heard of some of these names: MP2, MP3, AAC you may not have heard of, and we're going to talk about that, Opus and aptX. Now, the reason we go into this is so that you understand when you're setting up your network, you're going to run into these terms as some parameter choices, and we want you to understand what they are. Now, first of all, we can do audio without using compression, just basically doing something called PCM, which is uncompressed, just audio in its raw 24-bit 48K form, and this is the bit rate that's required to do audio uncompressed. So in many situations when we're doing multi-channel audio and video, this is going to be a factor of 10 or 15 or 30 of this number. So immediately your home internet might be a problem, and other networks that you have at your place of business might be a problem. So this is where audio compression solves this bitrate problem over slow and unreliable networks, because this also assumes a very reliable network, which we generally won't have using the internet. So now we jump into the various forms of audio compression. The first one is MP2. It had one goal: give us what we consider CD-like quality at 48K and give us a bit rate of 256 kilobits per second. And at the time, it was selected as a reference compression format for broadcast radio. Now, after MP2 became MP3. MP3 we've all heard of by now, but it had an objective to cut the bit rate in half. So basically 128 kilobits per second MP3 was to equal 256 kilobits of MP2. And that really became a standard that we still use to this day. Now, as audio and more complex audio has come out, there was a quest to make even better audio quality at a lower, or the same audio quality as MP3 at an even lower bit rate. And then we had something called advanced audio compression, which the acronym is AAC, and it was standardized in 1997. And again, it had its objective: increase the audio quality of MP3 and keep the same bit rate, or even lower. And from 97 to 2016, several flavors of AAC have emerged. And you're going to run into these terms when you're setting up a codec scenario. So that's why we go through this. And each one of these have a trade-off between bitrate, audio quality, and latency. So depending on where you are on the scale of bit rate and quality, this is where these various compression algorithms fall. Opus is another one that was introduced in 2012. Unlike AAC, MP2, and MP3, which have royalties that are paid in order to adopt those algorithms, Opus was developed as a royalty-free open source compression. So it's also widely used for doing complex audio from speech to music and doing it at a very reliable and doable bit rate. So let me put up a chart that shows you IP bitrate and encoder to decoder latency. This is the fastest bitrate requirement to the lowest or slowest bitrate requirement, and the various compression algorithms to do 48 kilohertz CD-like quality stereo audio. And you can see, obviously, PCM, no compression, requires the highest bitrate to do it, but the lowest gives you the lowest latency. And as we go down the chart and get into these lower bit rates, this is where we see various versions of AAC and also Opus. And of course, it does increase the latency, but this is perfectly acceptable in most cases. And it's a fixed latency. So if you're doing multi-channel, all the channels are in sync, just to be clear. But you can see this is why our industry tends to be in this range quite a bit when we have to use the internet. Now, we also have something called LAN audio. So many churches and live sound venues and install sound venues will take advantage of technology for LAN audio like Dante or AS67 or Livewire. These are technologies that actually have device synchronization because there's PTP, which is a precision time protocol. This can all be done over a LAN very easily. So Dante and AS67 and some of these other technologies have a means to see all the devices on the network. You have little controllers or control panels that allow you to connect them, but it's all done in the confines of a LAN or a local area network. But as soon as we go to a wide area network using the internet, that changes, and we need technology to broadcast and can make those connections. So who is the customer for this technology? Well, certainly traditional broadcast, radio, TV, OB vans, remote trucks. That's sort of obvious. Universities who want to broadcast events or lectures and connect campuses can use this technology, and we're going to show you more specifically how. Houses of worship would want to broadcast from their main location to satellite locations, and with the multi-channel codec technology, they can even incorporate all of the audio channels from the stage and all of the production that's going on and send up to 128 discrete audio channels along with 2-pop sync, and like if you're wanting to sync to video, and go and basically have the campus on the satellite side receive all those channels, remix it into whatever PA system is going on there. And it's a bidirectional connection, by the way. Public spaces can use this technology for background music, announcements, communications, and then just in general AV install, basically doing audio distribution over the internet. So if I want to connect a venue to another venue across the country, I can do that, and it'd be basically as if those two venues are working as one big audio network. So audio over a wide area network, point-to-point or point-to-many points, using the public internet. So when we do this, there's no quality of service because there's no guaranteed bit rate, and we have a limited available bit rate on the internet. Packets are lost, packets are duplicated, packets can be disordered, and there's also jitter, meaning that the packets are not received in a very timely manner. So what are the challenges that we need to solve to do reliable audio? Well, the first thing is we need to receive all the packets. Low quality networks are going to cause packet loss. We need to manage disordered and duplicated packets. We need to manage late packets, which is caused by jitter. We need to manage any clock drift between the sending side and the receiving side, or the encoder and the decoder. We also need to maintain, and we desire, high audio quality with a limited network bitrate. So what we'd like to introduce you to is a technology that's been developed and evolving since 2009. It's called Fluid IP. And it solves a lot of the IP challenges over unreliable networks. It's a smart IP streaming engine. It's built into every unit that I'm going to share with you. It guarantees quality of service, packets are fixed and reordered, and everything's managed. So all those problems that we wanted to solve have been solved. And we have the highest quality audio. we have excellent stability, we have, and this is a big one, the ability to do very advanced redundancy. So no matter what happens, we have a guaranteed signal at all times, and we can do it at the lowest possible latency. But as I've already shared with you, latency is a little bit of a function of the bit rate and the compression that you're using. So this technology, which is Fluid IP, was developed by a company by the name of Digigram. And Digigram is no stranger to audio over IP. They're actually the inventor of ether sound, which came out many years prior to the current AOIP technology that we use today. So they've been doing it for many years. So what makes Digigram's Fluid IP engine so unique? There's really three things, and that's all you need to know. The first one, it's one of the most adaptable solutions because all of those compression formats, remember that chart that had all of the different compressions and network bitrate and encoder to decoder latency? Well, you need to be able to have a full suite of selectability of various compression algorithms so that depending on your network, you can adapt it. So the fact that Digigram's Fluid IP has licensed all the available compression algorithms, you have the most adaptable solution. Number two, fixing the packet losses. There's something called forward error correction. So additional packets get generated at the encode side, and these additional packets are used by the decoder to reconstruct the stream if there's any missing packets. Now, the first thing you want to know is that you can dial in how much you want to use. You can use anywhere from 10 to 100% error correction. Now, obviously, as we use more error correction, we're sending more data, which means we got to have a higher bit rate to do it. And when we use error correction, we're also asking the decoder to wait for all the additional packets so that it can decode and reconstruct the stream. So the consequences of using forward error correction is that you need a higher IP bit rate and it's going to add latency. But it is a significant difference because the way in which this is implemented in Fluid IP and the ability to dial it in is very, very unique and very useful. The third thing that makes Digigram's Fluid IP unique, and probably one of the most significant, is this idea of 100% dual redundant streaming using spatial diversity and using time diversity, all part of the dual stream. The first concept is spatial diversity. Basically, the path that the audio takes is two separate paths over the internet. So we literally have to have two network interfaces with two separate IP addresses in order to do this and have true 100% redundant streaming. So Fluid IP gives us multiple Ethernet ports, network interfaces that we can configure and send our streams over the internet and have it take a completely different path. Then when it's received at the decode side, if something were to happen to the original stream, we have the duplicate stream. In addition to it taking a different path, which is what we refer to as spatial diversity, it also can be delayed, so with a concept called time diversity. And that means this stream can be delayed so that if there is a catastrophic event over the internet, we're not having it occur on the same datagram or packet sequence. So it's very powerful. So those three things, again, are most adaptable solution, forward error correction, and true 100% redundant streaming. In addition, the Fluid IP fixes jitter. It also manages the clock drift that we referred to. So what I'd like to do is show you an example of this. So here's a perfect example where we have a scenario. Could be a studio, could be a church, could be a venue, doesn't matter. We have whatever the audio is in this space. Could be network audio, could be analog, could be ASEBU, doesn't matter. We can go into one of the Fluid IP solutions, connect it to the internet via an internet service provider. It takes a separate path over the internet somewhere else in the world, receives that signal, and then we go out into whatever local audio format is going on here. But regardless, all the packets are received, disordered packets are reordered, late packets are managed, clock drift is corrected, and high audio quality is maintained no matter how unreliable the network. This is one example. Maybe a different example could be a home church to many satellite churches. So maybe we have Dante audio happening at the home church, and we're taking audio signals from the stage plus the the comms and IFB that's going on with the production crew. So all of that is audio, and that can all be piped into this box via Dante or Maddie or several other formats, but in this example, we're using Dante. We're sending that signal, all 128 channels, over the internet, 2 separate paths, receiving it, decoding it, putting it back out into Dante or whatever format we want, and then remixing it for this space. Meanwhile, any audio and IFB that we want to share back to the home church, that can be done as well. And then, of course, we can go up to many destinations from a single box. So in this example, we're just showing 2 satellite churches, but it could be many satellite churches. So these are just a couple of examples. There's more that we're going to share. So let's talk about the solutions, all right? They're pronounced IQOYA, Crosslink, which is typically written Xlink, so it's Crosslink and ServLink. There's essentially 6 solutions. They're very easy to understand because they all do the exact same thing. I've highlighted in red what the primary differences are, and that's going to be in the area of local audio connectivity and the number of audio channels or codecs that we can do over the web. So we have our basic unit, Crosslink LE. It takes a stereo input, and we can go out to another destination, very high quality, very reliable. We also can take that stereo input and go out to things like web radio. So this is a great way to do web radio, very affordably and very reliably. We have a Crosslink stereo, which gives us the added functionality of local controls on the front panel. So a lot of engineers prefer this one. If you want to jump up to the dual, it's like having 2 Crosslink stereos in a single rack. So we have 4 inputs or 2 stereo inputs and 4 outputs or 4 codecs over the web or 2 stereo, however you want to think of it. We can jump up to a Crosslink AS67, which means all of the I/O in and out of the box is AOIP. So it's AS67 Ravenna Livewire, and then we can go up to 16 codecs over the internet and receive somewhere else. The Crosslink MPX is more for doing FM transcoding, so taking FM signals and sending that over the web and then receiving it and it being in FM format. It's going to be more for radio applications. And then I've highlighted the IQOYA ServLink because this one is a very special piece. And when I say special, I mean because it can do so many things for you. Number one, it'll do up to 128 codecs over in a single rack space. It will also take various local ins and outs via Dante, Maddie, ASEBU, analog, as well as Ravenna connectivity. So it's a very powerful box for when you want to use the internet as a digital audio snake. And I'll show you some examples of that. So IQOYA has been used for well over 10 years. There's over 10,000 codecs in operation worldwide every day. This has been going on since 2009. It's also ST2110 compatible. These products support all of the pro audio formats that are used in live and studio and broadcast. These are just some of the companies that utilize this technology. So you're in very good hands with IQOYA because a lot of folks that use this technology need very reliable and stable streaming. And so that's why we like to put this up, just so you know the types of folks that have tested and certified using this technology. Let me show you the back panel of a typical box. So we would have our analog and digital ins and outs that we would normally expect. Since this unit is a dual, the second set of IOs is found on a multi-pin connector. Now I've highlighted the fact that there are separate networking ports as well as an SD card reader. If I were using this box in a distribution mode where I'm receiving audio from the studio and this is at a transmitter site, it's nice to have an SD card because if we were to lose internet for any reason, we can have a preset playlist ready to go and that will keep the station on air. The other thing that I've highlighted is the fact that these come with 4 networking ports for full separation of IP traffic. This is a huge, huge difference between the IQOYA Fluid IP technology and many other solutions. I can configure one of these ports to be my local AOIP, like AS67. I could then configure 2 of the ports to be one being my primary ISP and the other one being my secondary ISP for that true redundant streaming that I was talking about. That's why it's such a big deal. And of course, we have redundant power supply, metering, headphone, all the things that you would want. And you could administer this directly on the front panel. You also could administer it by just going to an IP address directly in the web browser on the network that this is connected to. So let's talk about the Serv link. It's the same technology. The only difference is it's got a very high-end multi-channel capability, meaning it's got a high density of audio channels, audio in, audio out, and the number of codecs that you can stream over the internet. It comes in several flavors. So we have Dante and Maddie, AS67 and Ravenna, ASEBU, ASEBU and analog together or just analog. So it's pretty powerful. So what I'd like to do right now is play a video of showing you some of the ways in which this could be used. As you can see, that's a very powerful solution. And here's a nice little diagram of the types of versions you can get. Many folks will get the Maddie version or the Dante version if they're dealing with like in a house of worship setting. But in other settings, you might go with AS67 or Maddie and AS67 or ASEBU only. And it comes with 8 codecs, and you can scale it. So I literally, if I only want to send 16 channels somewhere, I don't have to pay for codecs I'm not using. So when I get a Serv link, for example, it comes standard with 8 audio codecs, even though Maddie and Dante and these formats can give me 128 channels of ins and outs. So I can, with a software update and a Digigram dealer, I can get those software updates and scale it up to 16, 24, 32, all the way up to 128 codecs. So I can get the unit that I need for exactly the needs that I have. Now, usually about now, I like to re-display this slide because when you start thinking about 128 channels of audio, even if we're doing Opus, you know, so we're talking about 64 stereo channels. So 160 times 64, you know, that becomes a much bigger situation in terms of IP bitrate. And then our latency performance is again redisplayed here because a lot of people start thinking, okay, well, what kind of network do I need to have to do those kinds of channels? Well, again, using these various compression algorithms that are available to you, most networks will accommodate it just fine. If I'm trying to do PCM, that's a different story. What about network security? Because that comes up. You know, if we're doing audio over a network and we have a local network with Dante on it or AS67 and we're connecting that to the internet, we don't want our codec to be a breach. So typically we would set up a network that looks something like this where our codecs are somewhere out on the outer firewall, the DMZ layer. Each layer is protected if we have trusted and privileged information further in the network. And security is properly maintained via these incremental firewalls. And, should the DMZ located equipment be compromised, deeper levels are not accessed. But what if we start enabling technology like AS67 and Dante? Well, in those situations, we have to often sit the codec further in the network behind these other firewalls. So it's now in the trusted, possibly even the privileged data area of the network. And the audio codec can become a network vulnerability spot if we're not careful. So what Fluid IP has done with Digigram, what they did is they've separated the Ethernet ports. So the Ethernet ports responsible for each world are no longer connected. Only a PCI bus internally connects them. So you can't breach the network if you get through via the WAN side. Now, everything we've talked about up to this point has been in the context of studio codecs in the front of house position within our broadcast facility or whatever. But let's say we want to do broadcasting remotely, either out on a missions trip, or if this is a radio scenario where we want people to be able to broadcast out in the community. If this is a university and they want to broadcast events. And again, we can broadcast events not only to radio stations and transmitter sites, but we can also broadcast events via web radio, which is very easy to set up. Let me show you this IQOYA Talk portable codec, some things that it can do, and then we'll get in more detail. So this is a very powerful solution. And, you might be wondering, well, there's other ways to do streaming via software codecs and other things. But again, I want to emphasize this is high quality, very reliable audio, like, when you're broadcasting a football game or something like that. These are very good quality connections, which can be used in a lot of various scenarios. Now, this is an all-in-one solution because it has all of the mixer functions that you would need, and it's pretty much all you have to carry around is like you saw in that video, in the backpack or in the case, an IQOYA Talk, and it has pretty much everything. It's portable, it's easy to use as a smartphone, has battery power, even has internal recording so that you can record directly in the unit. So you can use it for podcasting, offline recording, as well as on-air recording and playback. Pretty powerful. Now, a typical setup would be something in the field over either 4 or 5G or Wi-Fi or Ethernet, connecting back to a destination, referred to as the studio in this example. And we can have two-way communication. So we can have a program side, two-way communication, and we also have a completely separate side for talkback. And depending on what box we put in this position would achieve that. So pretty powerful. Now, all of the connections were sort of reviewed in the video. I just want to point out the onboard recording capability. the ability to access the recordings via the back panel through the USB-C. You can connect to your laptop, access recordings. You can also put recordings on there. In addition, the battery compartment. This comes complete with all of the connectivities, the 3G, the Wi-Fi, all of that's built in. There's no options. All you have to supply is a SIM card, which you can get from your local cell phone store. It does come with one lithium-ion battery. You can actually use two, so that'd be the only accessory if you want to buy a second battery or the carry case. Otherwise, it's a complete solution all by itself. Very portable, very powerful. Now on the back, I'll show you the cell. You got two cellular antennas, very powerful, as well as your Wi-Fi antenna, Ethernet ports. If you have a local network, you can connect directly to it. You can even power your cell phones while you're on air. USB-C for connecting to the actual internal drive, power supply, GPIOs if you want to trigger events to take place, and then you have auxiliary ins and outs like you saw in the video. So you can use an external mixer for more inputs. You can also configure this to be ASCBU digital in and out. And then you can create a mix. If you're doing something local, you can use this as a mixer and send it out to a small PA, no problem. So what I'd like to do is do a little bit of a live demonstration of how this works. And I'm going to just illustrate doing a very reliable remote connection with two separate manufacturers' codecs simultaneously, which is pretty cool. In this example, we're going to use a Comrex Access, and we're going to use a Digigram IQOYA Crosslink Dual, which is very powerful. And what we're going to do now is let me show you that demonstration. So as you can see, that's a very powerful solution and pretty easy to use even for non-technical people. Now we've showed you the studio codecs and we've showed you the portable codec. There's one last piece of the puzzle I want to present to you for doing reliable audio over unreliable networks, and that is a newly launched technology called IQOYA Connect and IQOYA Guest. Now IQOYA Connect is a Digigram SIP infrastructure that will host IQOYA Guest if you're using IQOYA Guest, but it also gives you third-party interconnectability, or what we call interoperability between third-party codecs. And IQOYA Connect can also be a web application that allows you to monitor your codecs. Now, if you're a broadcast facility, this is going to be very helpful and useful for you. If you're a university or an organization that's using several codecs, this is very helpful. If you're a church or you're doing simple connections from A to B or one point to many, you might not need the monitoring capability. But this is where it sits in the infrastructure. You might use IQOYA Connect to manage, monitor, and remote control everything that's going on. And IQOYA Guest is a situation where I can have somebody remotely who doesn't have any hardware, doesn't have to install any software. We can send them a link, and it turns their web browser into a codec that can connect to our infrastructure. Very powerful. Now, the product I want to show you was something that was developed in the early part of 2020 in response to the COVID-19 pandemic called IQOYA Guest Preview. IQOYA Guest Preview then evolved into IQOYA Guest. But I'm going to talk about IQOYA Guest Preview. 4 problems, 1 solution. We want to have somebody on air who doesn't have any technical knowledge, who doesn't have any equipment, and there's no engineer that's available to help them get set up. So what's been developed is a simple link that can be hardwired to our channels of our codec, and we send it to somebody remotely, and they click on it, opens up a web browser, and now it establishes a communication, very similar to like Skype. And we can have a two-way communication between those two situations. So let me show you a demonstration of that. Now, IQOYA Connect is the SIP infrastructure that allows all of this to happen. So let me just give you a quick little illustration of this. Now, what I want to do is show you how this works. So I've literally gone to the link, which is going to make a call into my Crosslink, which is in the studio, and that's got music and dialogue and things going on. You'll notice over here we have the options to choose what our streaming option is going to be, stereo or mono. So if I wanted to come in both left and right on the stereo codec, I can. If I do choose mono, then of course it would come in on the left channel. I also can choose which bitrate I want, and then if I need to, I can use included DSP as part of IQOYA guest echo cancellation, auto gain control, noise suppression, and high pass filter. Now, since I'm on my laptop, I'm connected to an audio interface, so I will see that here as well. Otherwise, I would just use the internal microphone. And making a call is as simple as tapping the call button. And now we have a connection to the studio, and we're listening to audio coming back from the studio. This could obviously represent somebody's talking to me. And then to hang up, we simply hang up on the call. So it's pretty easy if you're a non-technical person. And that is IQOYA guest. Thanks for watching. So pretty simple, very easy. And there's versions of that depending on the browser that you use, where you actually have a mixer and you can preload audio files to play back to the studios, all kinds of things that you can do. And if you want more information on that, definitely reach out to us, and we'll show you all that you can do with that. So let me show you what you can achieve with some of these various application setups. We talked a lot about, this basic broadcast environment, and, with broadcast coming home and lots of folks streaming and broadcasting from home, this is a great solution where you can use, a combination IQOYA talk with an IQOYA crosslink and do very high quality radio quality, satellite radio quality broadcasts, sending and receiving signals, either doing it live or taping it, however you want to do it. In addition to that, many musicians want to stream audio out to the internet and have an audience and do it a lot more reliably than doing Facebook Live and YouTube Live and things like that. So using a simple crosslink, I can connect my normal connections that I would do at a live gig into the back of the crosslink, set up a free web streaming account, caster.fm is one example, and provide a link to my audience, and all of my audience can log on to that link and listen, and it's going to be a high quality web radio experience. It's not going to sound like your typical software codecs that you use. And the connection between your home and the web streaming service is going to be very rock solid based on the Fluid IP engine that we talked about. Let's say House of Worship. I think we showed a video that showed how we can do 128 channels of bidirectional audio, which could not only include the actual service audio, but any IFB and communications that's going on. This could also be a venue like Madison Square Garden connecting to the Staples Center and another venue. And even though all of these venues have their own audio networks, we can interconnect them and use the internet as a digital audio snake. Another application might be doing lectures or very high quality audio centric lectures where we're talking about, classes that require audio to be very well done without dropouts, could be private music instruction, could be all kinds of applications. So we might have something like an IQOYA at the university, all our students on IQOYA guest dialing in. We can actually use an audio interface with a mixing feature to do any mix minuses. So here's a campus lecture with remote students. Here's a situation where we're just changing up the audio interface, but it's the same application. Or maybe it's a college of music or a private instructor or a professional musician that wants to be able to hear in very good quality the artist remotely. Perhaps the lecture is taking place remotely and the university is shut down, kind of like during the COVID-19 pandemic. And the instructor can also be using IQOYA guests. And all of these folks can have a very high quality audio share between their music or whatever multimedia is going on. Another way to do it is with web radio. You could basically do a web streaming scenario where this could be an offsite translator via IQOYA guest is listening and then translating in real time out to people in a different language. There's lots of different ways to use this technology. Or when I grew up, we just sat in a lecture and didn't really talk. We just listened for an hour. So the teacher can do web radio in parallel to video very easily. You can just have a web browser open for the audio, have another tab open for the video portion and just mute the audio, but you'll have a much better audio experience. It's very hard to pay attention to a lecture when the audio is not so great. And then let's say just a campus scenario where you have maybe folks contributing to a lecture remotely into the university, plus what's going on locally in the university, and then that all going out to web radio. It's another way to do it. And my favorite is just a campus-wide, all departments taking advantage of an investment and a technology, because many schools have athletic departments, and they want to broadcast their games, so they could now broadcast their games over web radio, and all the parents and students that are not local can listen to the games. Meanwhile, we're doing lectures and other university events. So with something like a Serv link, we can do multiple different broadcasts all at the same time, but they're different programs. Not a problem. Very, very possible. How about a remote translation case? Maybe in the conference center, we are doing something in one language, and we have remote translators logging in with IQOYA guests, listening to the original meeting or event in English, and then simultaneously translating it, and then sending that out to web radio, and then we can do English, Spanish, French, for example. Very powerful stuff. And then we have our traditional radio and TV uses, where we might have something going on in the studio and over 2 separate network paths going to our transmitter site with redundant streaming, doing multiple codecs and multiple programs from the same company. Many companies own several radio stations now, and they broadcast all the different stations out of the same facility. So having multiple codecs and multiple audio channels makes that possible. Also, we can take satellite, which is a type of signal that we can deal with along with local audio, and with transcoding, resend it out to various distribution points. We can do streaming programs to various programs. So we might have something coming in, going out to web radio, simultaneously in a different format going to our satellite, and then simultaneously in a different format going to other transmitter sites. We could do terrestrial distribution. This is what Apple does. So you could take audio programs and go out to several partners throughout the world at the same time, and simultaneously record and encode network programs while streaming to live partners. Very, very powerful. Web radio, very simple to do. Web streaming service with a high quality audio codec. Also, we can do satellite backups with IP. So we have our original satellite, but then we can also do a backup using IP. Very, very cool. So I hope this gives you some ideas of the solutions and the power of Fluid IP, and how that you can achieve high quality, reliable audio over unreliable networks. So I'd like to thank you for your time and your attention, and thanks for watching.